Hello and welcome to the Unit 1 lecture on Section 5.1, which deals with electrons.
So here we are again. I'm Mr. Lin.
I'm Mr. Sakaguchi, and here we go. So the nuclear atom, after, if we remember back to our model of the atom, we left off at Rutherford, and he had done his gold foil experiment and identified the nucleus, and the electrons kind of just sit around on the outside. While the nucleus is well defined, it left many questions concerning the electrons, some of which are listed here. So how are electrons arranged around the nucleus? Why aren't they just sucked in and smack into the nucleus? And why is that all that open space necessary? How do electrons account for the behavior chemically and physically of these elements?
So they had all these questions about where the electrons are, what they did, why they worked the way they worked, and they were able to find the key to answering these questions by the fact that electrons or elements gave off light when they were energized.
Now you have to remember here, when we're talking about chemical reactions and things like that, we know that the identity of the element doesn't change during a chemical reaction, so that leaves the protons and the neutrons out. So the only thing that could be changing as elements combine to form different kinds of compounds are electron behavior. So the rationale behind this is if we understand the arrangement of electrons, we can therefore understand why these elements behave the way they do chemically. And again, light, as we've talked about, was the key at this point in terms of trying to figure out how these electrons were arranged and why they behave the way they do. So if we're looking at light before we look at electrons, the thing you have to know about light is that light has some wave-like properties. Light is not the only kind of energy that has wave properties. Light is part of a larger
Spectrum.
known as the electromagnetic radiation spectrum. So basically, all kinds of energy exhibits this wave-like behavior as it travels through space.
So it's not just visible light, but we're talking about things like radio waves
We'll get to that in a second.
and such.
So let's first identify what the components of a wave are. And the figure below kind of illustrates some of the basics. Some of the stuff you might have seen in your previous math class, depending on what math you're in. One idea is wavelength, which is this green arrow. This is lambda. This is basically the distance from one peak of a wave to the next peak immediate to it. What we find is all electromagnetic radiation, including light, moves at the speed of light, which is 300,000 kilometers per second. Period is basically the time between going from one part of a wave to the next part where it begins to repeat itself.
Then you also have the frequency, which is how often a crest or top of the wave passes through a point in space per unit of time. So how often something happens. And then there's also the amplitude, or how high that wave peak hits.
Right. One other thing to sometimes instead of calling it crest to crest, sometimes we'll call so for instance, if you follow my arrow, I'm tracing a wave, right? So notice once I get to the next end of the green arrow, if I continue, the wave begins to repeat itself. So following the path from here to the corresponding peak on the next wave cycle, it represents one wave cycle. So sometimes frequency is referred to as the number of wave cycles per unit time as well.
So first up we have the wave equation, which deals with the three variables of speed of light, wavelength, and frequency. You'll notice here the speed of light is abbreviated to a different form, 3.0 times 10 to the 8 meters per second. That's the one that's more commonly seen. What to take away from this is that wavelength and frequency are inversely proportional. When one goes up, the other one goes down. Okay, so the lower the frequency something is, the longer the wavelength will be. So low frequency, long wavelength, high frequency, short wavelength. And this is because when you multiply the two together, you get the same speed of light for all EM waves.
Okay, let us continue. I have nothing to add. This figure here kind of represents the electromagnetic spectrum. So you can see visible light makes up a small portion. Radio waves, which you're familiar with if you listen to the radio in your car. Whoops. And you also have microwaves, which we use to heat our food.
Yeah, burritos.
Infrared is used for remote controls. Microwaves, aren't they also used for cell phones?
Yeah, microwaves, cell phones, same thing.
We have UV light, which most of you guys are trying to protect yourself from so you don't get sunburned when you go to the beach. And then when we go to the dentist, we have our X-rays, which are actually manufactured, and we'll talk more about that later. And then gamma rays.
Gamma rays are the really dangerous ones. When they talk about radiation and radiation sickness, it's usually due to the gamma rays, and no, it's not going to turn you into a big green monster.
One other thing to notice is that notice how the wavelength in meters is decreasing, but see how the number of wave cycles or frequency is increasing as we go from left to right? So that's something to keep in mind as well. Also notice that different colors of light will have different frequencies and wavelengths as a result.
So the longer wavelengths are going to belong to the red light, and the shorter wavelengths will belong to the purple light or indigo. This has to do with also the amount of energy that's being outputted.
And one of the things you're gonna need to know how to do are how to do some calculations involving wavelength and frequency. So this one is a worked out example. So here we have a microwave. They've given us the frequency. The units for frequency is hertz. Sometimes you'll also see, I may use my pen here. No, that's fine. Sometimes you'll also see seconds to the -1, which is also another unit for frequency.
The hertz measurement, by the way, means cycles per second.
A lot of you guys who are into computers, you might recognize it as a way to measure processing speed.
Right, like how many computations can be done per second.
So when we're doing this kind of problem, there are 3 simple steps you can follow. So identify which equation to use. In this case, we only have really one equation that we've learned so far. So we're going to use our wave equation. Then we're going to define what we know and what we don't know. So we're going to assign values to our variables.
So with the first one, with the wave equation, always the speed of light is constant, 3 times 10 to the 8 meters per second. And in this problem, the wavelength is unknown. That's what we're solving for. And then finally, the frequency is given at 3.44 times 10 to the 9th hertz, or in this case, cycles per second.
One other thing to note here is the units here. Okay, so notice how this is in seconds to the -1 or hertz, and this is in seconds. So if we multiply these together,
or actually when you wind up dividing
sorry,
them
we're
out.
going to divide
Yeah.
this. When you divide them together, seconds will cancel out. In other words, seconds, like just as a quick lesson in dimensional analysis. Most of you guys know, like if we're doing algebra and I get x over x, the x's cancel out, right?
And that winds up equaling
it ends up equaling 1.
1. Yeah.
Similarly, when we end up dividing, we're going to end up with seconds in the numerator and the denominator, which means they're going to algebraically, just like x, cancel out.
Right.
The unit we're going to be left with is meters. So our wavelength will have the final unit of meters. Okay. When we do some advanced problems in class, sometimes you might not have this unit. Okay, maybe you're in kilometers or nanometers or something else, and you might have to do some conversion, but we'll work on that in class. So once we have our variables and we've defined them, all we need to do is, just like an algebra class, substitute and solve.
Right. So then in this case, we plug in the numbers, and then to solve, we want to isolate the unknown variable, in this case wavelength. And to do that, we divide both sides by whatever is being multiplied by wavelength. In this case, the frequency. So we divide both by the frequency value, getting us our wavelength. Now notice in the name wavelength, length being a measurement of distance, and so we have that here with the meters. That'll help you make sure that you have the right answer and the right units at the end.
That's right.